In our last lecture, we went through some considerable pain to come up with a pretty complicated expression for the running time of a very simple algorithm. So our algorithm was this sequential search algorithm. What does sequential search do? It takes an array and a search key, and then it goes through the array index by index, looking for the search key, and when it finds the search key in the array, it returns that index. If it doesn't find the search key, it returns -1. And so what we did is we took this sequential search algorithm, we derived the kind of a complete expression for the running time of this algorithm, TSS of n, where the running time was expressed as a function of the input size. So there's the time, there's the input size, and the expression looked something like this. So it looked like n times t1 plus t2 plus t3 plus t0 plus t1 plus t4 plus t6, right? And then this was, in particular, it was the worst case running time, so the running time that would result if we gave it the worst input we could think of. And it's this kind of horrible expression. And so if we have a simple algorithm and that gives us a horrible expression, that feels like bad news for the rest of the course. Fortunately, the question that we asked about this expression gave us a simple answer. So recall the question that we asked was, what happens to the running time if the input size doubles? So I'll just write it simply like this, sort of informally. What happens if we go from an input of size n to an input of size 2n? So our question is, what's this look like? Particularly, what's this look like when n is very large? And so I'll just write in parentheses here, I'm taking the limit of this thing as n approaches infinity, question mark. And the answer that we came up with to these two questions, what happens when the input size doubles, is that the running time basically doubles, right? We get this times 2 effect on the running time. And so if we look at this expression carefully and ask what of this expression would give us this answer, we'd find that we could simplify the expression down considerably and arrive at the same exact answer without worrying about all of these T1, T2, T3. And in particular, what I want to focus on is this term right here. So if you look back at the previous lectures, what we found was that T2 corresponded to the search key comparison, as I recall. So T2 corresponded to this operation. It corresponded to checking this. Is the element at index I different from k? Right? So T2 is the time it takes to compare a search key. And if we simplify this expression, this expression and basically just ignore all the rest of these operations, we would get the same answer. So here's the core idea of algorithm analysis that's going to simplify our lives considerably. So the idea is we get the same answer if we just look at one key operation that we would get if we looked at every operation. So I'm going to write this out to make sure that this is cemented in your minds. So the idea is often we get the same answer from one, we call it the one basic operation. One basic operation that we would have gotten from the whole complete formal analysis. All right, and I'm going to put this in a box because this is one of the key ideas that'll enable a lot of analysis in this course. Okay, so what this means is that what we'd like to do when we're analyzing algorithms is find this basic operation, so find the key little line of pseudocode in an algorithm description that gets executed the most, and then analyze the whole algorithm from the standpoint of that algorithm, right? So our plan for analyzing an algorithm is going to look something like this. So the plan of analysis. It's going to look something like this. First, we want to identify the input size. So we want to come up with an expression for the input size. So identify, and I'm just going to call this n. Identify n input size. Two, we want to identify the basic operation. So ditto marks there. Identify the basic operation. And then 3, proceed with the analysis. So 3, derive t of n, where t is the running time. Here, I'm going to even call this, it's not the running time anymore because we're looking at the basic operation. T is now the number of times the basic operation executes as a function of the input size. So this is the number of basic op executions, and n is the input size. And going forward, this is going to be the core approach that we'll take with every single algorithm that we look at. And whatever we are doing, we always want to make sure that these 3 bullet points have a place in our analysis. So the issue is, the only thing that we've left off this list is, what do I do with t of n, right? And so this, we have to go back to some of the concepts we talked about in the last lecture, and we have to ask the following fundamental question for, what is the order of growth of t of n? Order of growth of t of n. So what does this mean? What is the order of growth? Well, we asked this in an informal way last time when we were asking the question, what happens when the input size doubles? But what we really need is a complete, comprehensive, formal way of asking this question. And so this leads us into the topic of this lecture, which is big O. So some of you may have heard of big O before, but today we're gonna define it very formally. We're going to define a few companion metrics that are similar to big O, and then we're going to go from there and start working some examples.